Let's walk through the journey of prenatal hematopoiesis, the process of blood cell formation before birth. At conception and the earliest stages, blood cell production begins in the yolk sac. This is the very first site of hematopoiesis. Its role is temporary and fades quickly, disappearing by the end of the first fetal month. Next, the liver takes over as the dominant hematopoietic organ. Starting around the second month, the liver becomes the main blood-forming site, peaking in activity during the third to fifth months. This phase is critical for building the developing blood system. The spleen also participates, beginning around the third month. Its role is supportive, and while not as dominant as the liver, the spleen contributes significantly during the mid-gestational period. Its activity gradually decreases after the fifth month. By the fifth month onward, the bone marrow begins to assume responsibility. Its activity steadily increases, becoming the primary hematopoietic site by the seventh to ninth months, and continuing after birth as the lifelong center of blood formation. Meanwhile, the lymph nodes begin to contribute around the fifth month, though at a much smaller scale compared to the liver or bone marrow. Their role is tied more to immune system development than bulk blood cell production. Key sequence to remember: yolk sac to liver, then from liver to spleen, then from spleen to bone marrow, with lymph nodes joining later. This smooth transition ensures the fetus has a continuous and reliable supply of blood cells throughout development. In adulthood, hematopoiesis, the production of blood cells, takes place primarily in flat bones. These include the skull, the sternum, the pelvis, the ribs, and the vertebrae. These sites house red bone marrow, which contains colony-forming units. The progenitor cells responsible for generating red blood cells, white blood cells, and platelets. Unlike in prenatal life, where hematopoiesis shifts between several organs, in the adult, the process is largely restricted to these flat bones, making them critical reservoirs of blood cell production. Let's go step by step through heme synthesis. Heme synthesis requires two essential components: iron and protoporphyrin. Both must be available and properly balanced for red blood cell production and function. Iron is tightly regulated in the body. Transferrin is the transport protein that carries iron in the bloodstream. Ferritin is the major storage form, a soluble protein that safely holds iron. Hemosiderin is a water-insoluble storage form, usually used for long-term iron deposits. When iron accumulates beyond storage capacity, it can deposit in tissues and organs. This may cause hemosiderosis or, in more severe cases, hemochromatosis, leading to organ damage. The other key component, protoporphyrin, is produced through a series of biochemical reactions involving multiple precursors. When these pathways are disrupted by enzyme deficiencies, a group of disorders known as porphyrias arises. In porphyrias, heme precursors build up, causing characteristic symptoms and red or port wine-colored urine. Porphyrias are classified based on the stage of precursor accumulation. Early precursors such as delta-aminolevulinic acid and porphobilinogen are associated with neuropsychiatric symptoms. An example is acute intermittent porphyria, or AIP. Later precursors such as uroporphyrin, coproporphyrin, and protoporphyrin cause cutaneous symptoms. These include photosensitivity and the development of excessive facial hair. In summary, heme synthesis requires both iron and protoporphyrin, and disturbances in their pathways, especially in porphyrias, can present with either neurological or cutaneous manifestations. Let's go over the sequence of heme precursors with a simple mnemonic. To remember the order, say, while in the delta, pour your cop, Pronto, a cup of heme. This phrase helps you recall the pathway. Delta-aminolevulinic acid comes first. It is followed by porphobilinogen. Next is uroporphyrinogen. Then coproporphyrinogen. After that, protoporphyrin. Finally, protoporphyrin combines with iron and globin chains to form heme, the functional component of hemoglobin. Now, an important clinical note. If any enzyme in this pathway is blocked, porphyrins accumulate, leading to a group of disorders called porphyrias. These may cause red or port wine-colored urine and various symptoms. Also remember, certain steps in the pathway are marked by a star, meaning they are sensitive to lead poisoning, which inhibits the enzymes and disrupts heme synthesis. In summary, the mnemonic, delta, por, cop, pronto, heme, captures the sequence of precursors, while also reminding you of the clinical consequences of enzymatic blocks or lead inhibition. Let's break down the hemoglobin-oxygen dissociation curve and what it means when the curve shifts. The hemoglobin-oxygen dissociation curve describes how readily hemoglobin binds oxygen in the lungs and how easily it releases oxygen to the tissues. When the curve shifts to the left, hemoglobin binds oxygen more tightly. This means oxygen is not released adequately to the tissues. As a result, even though the blood may carry plenty of oxygen, the tissues may not receive enough, leading to reduced oxygen delivery. When the curve shifts to the right, hemoglobin releases oxygen more easily. This enhances oxygen delivery to the tissues. It ensures that active tissues which require more oxygen receive it efficiently. In summary, a left shift means oxygen stays bound to hemoglobin and tissues are deprived. A right shift means oxygen is released more readily, improving tissue oxygenation. Let's walk through the hemoglobin-oxygen dissociation curve for learning reinforcement. The x-axis represents the partial pressure of oxygen in tissues, while the y-axis shows the percent saturation of hemoglobin with oxygen. The normal curve follows a sigmoid shape, reflecting hemoglobin's cooperative binding of oxygen. Left shift. When the curve shifts to the left, hemoglobin binds oxygen more tightly. This means oxygen is not released as readily to the tissues. Situations that cause a left shift include decreased carbon dioxide, increased pH or alkalosis, the presence of fetal hemoglobin, which has a higher affinity for oxygen, multiple blood transfusions, which reduce levels of 2,3-diphosphoglycerate, DPG. The consequence: tissues may become oxygen deprived even if blood oxygen saturation appears high. Right shift. A rightward shift means hemoglobin releases oxygen more easily to the tissues. Factors that promote a right shift include increased carbon dioxide, decreased pH or acidosis, increased 2,3-diphosphoglycerate, DPG, which weakens hemoglobin's hold on oxygen. The benefit: tissues, especially those with high metabolic activity, receive oxygen more efficiently. Key takeaway: left shift. Oxygen stays bound, poor tissue delivery. Right shift. Oxygen is released, enhanced tissue delivery.